All right, let's go ahead and start our next lesson, our next unit, which is on electrochemistry. And so what we're going to look at is a couple different types of what are called electrochemical cells. The first type that we'll look at is, now this is actually should be like a slash in here maybe, voltaic or galvanic cells. It's not voltaic galvanic, it's a voltaic cell or a galvanic cell. An example of this type of electrochemical cell is a battery. And let me kind of give you a brief overview and then we'll go through this particular one. So basically in a galvanic cell, you have a spontaneous redox reaction that occurs. I'll explain what that means in a little bit. And that reaction produces electricity, just like a battery. All right, so let's go ahead and draw this diagram. Pause the video as needed. So what we have is we have two beakers, each with a particular solution in them. And then we have a metal, a different metal, submerged in each of those solutions. These metals are attached with wires, so these squiggly things here are wires to this measuring device here. And then the two beakers are connected to each other with a U-shaped piece of glass tubing that has something in it. So for this particular galvanic cell, the metal on the left is copper. And the copper is in a solution of copper 2 nitrate. And so what's important to know here is the composition of this solution. So we have all kinds of copper 2 ions in solution. Of course, there's nitrate ions as well, but the nitrate ions are just a spectator ion. On the right side, the right half cell it's called, we have a piece of silver metal. And the silver metal is in a solution of silver nitrate. So again, we have lots of silver ions in the solution. Once again, nitrate is a spectator ion. So notice we have always, and this will always be the case, a metal in a solution of one of its own ions. The piece of glass tubing that's connecting the two solutions to each other is called a salt bridge. And so usually there's a piece of cotton or something here that prevents the solutions from coming out. And that salt bridge is usually filled with, well, it's always filled with a solution of a salt, but that is often potassium nitrate solution. We'll talk about the function, purpose of the salt bridge in a little bit. Lastly, the pieces of metal are connected to a measuring device, something that measures some property of electricity. Can be a voltmeter, which measures voltage. Could be an ammeter, which measures current. And we'll talk a little bit about both of those in just a bit. All right, so let's say that you put all of this together and you let the reaction go. So what happens? So I'll be flipping back and forth to this diagram. So what happens is that electrical current flows from the copper metal to the silver metal. What is electrical current? Well, electrical current is essentially electricity. What is electricity? Movement of charged particles or movement of electrons. So we have electrons being transferred from one substance to another. Therefore, we have a chemical reaction that occurs. So let's label on our diagram the direction that the electrons travel through the wires. So we have electrons going this way. Now, how do we know the electrons are going from the copper to the silver versus the other way around? Well, one of the ways we know is based on the observations that we are given. So later on, you will be able to determine for yourselves what direction the electrons travel through the wires. For this one, I'm telling you. All right, some observations. So let's say you let this reaction go for a while, and then you take it apart and you measure the masses of the metals, the copper and the silver. So you notice that the mass of the copper metal, which by the way is called an electrode, so the metals that are attached with wires to the voltmeter are called electrodes. They have special names, which we'll learn about in just a bit. The mass of the copper electrode decreases by 2.00 grams. So let's say it started off with 15-gram piece of copper metal, let the reaction go for a period of time, take it apart, remeasure, and now we see that the mass is 13.00 grams. So it's gone down by 2.00 grams. Another observation is the mass of the silver metal, which happens to be the other electrode, increases by 6.80 grams. Also, the solution that contains the copper 2 ions becomes darker blue. Now, these changes should tell you a little bit about what's going on in this reaction. So, what does the decrease in the mass of copper and the increase in the mass of silver have to do with this reaction? Well, let's take a deeper look. Let's go ahead and take the mass change of each metal and convert that to moles. So take the 2 grams of copper, convert that to moles. Take the 6.80 grams of silver, convert that to moles. Go ahead and pause the video and do that now, please. All right, hopefully this is what you got. So we have a change in moles, 0.0315 for copper and 0.0630 for silver. Notice anything about those amounts? Take a deeper look at those numbers. All right, we'll come back to that in just a second. All right, let's do this. Let's write equations for what's occurring in each beaker. Again, each beaker is known as a half cell. Why? Well, the whole thing is called an electrochemical cell, a galvanic cell in this case. And so half of that galvanic cell is called a half cell. Interestingly, I'm going to skip ahead to letter C for a second. The processes that occur in each half cell are known as half reactions. Again, they are half of the overall reaction. They cannot occur all by themselves. They need to occur together. All right, so in the beaker on the right, or in our right half cell, we have silver ions being reduced. Remember, we talked about this a while back, earlier in the year. These silver ions are gaining electrons to form silver metal. The copper metal is being oxidized. And again, I'll explain what these terms mean in a bit. We have the copper turning into copper 2 ions, and we have electrons that are being lost. Those are shown on the right side of the equation. So remember, when something is gaining electrons, the electrons that are gained are shown on the left, and if something is losing electrons, the electrons that are lost are shown on the right. So let's go ahead and do this. Let's take those two half reactions and combine them and get our overall equation. So again, let's take a look here. We got Ag plus an electron makes silver metal, and we have copper metal forming copper 2 ions and a couple electrons. Well, here's the deal. We have 1 electron being gained and 2 electrons being lost. That does not make sense. The number of electrons gained and lost must be the same. So I'm going to take this half reaction here and make sure we have 2 electrons. Well, how do we do that? We're going to multiply everything by 2. Now we have 2 electrons gained, 2 electrons lost. Those are going to cancel. Let's see what we end up with. We have 2Ag plus Cu makes 2Ag plus Cu plus 2. This is our balanced redox equation, it's called. So redox, this term here, is short for reduction and oxidation, or oxidation and reduction. Again, I'll explain in a minute what those processes actually mean. Notice anything about the amount of copper metal that reacts compared to the amount of silver metal that is produced? So something to be careful of and mindful of is what happens to the amounts of the reactants. These are the reactants during the chemical reaction. What happens to their amounts versus what happens to the amounts of the products during a chemical reaction. So we said that the mass of the copper electrode decreased. Well, of course, it's a reactant. And we also said that the mass of the silver electrode increased. Well, of course, it's a product. And also the solution containing the copper 2 ions got darker blue. Why? Well, we're making more copper 2 ions as a result of this reaction. So the concentration of copper-2 ions in that solution is increasing, making that solution darker blue. All right, so let's take a look at some important concepts in regards to electrochemistry. All right, so though we can write separate equations for our half reactions, each half reaction cannot occur alone. Basically, you cannot have something gaining electrons without something else losing electrons. So, got to have them both. Electrons are shown in each half reaction, but as we just saw, though, never, ever, ever in the overall equation. So the electrons have to cancel. We're going to see them in each half reaction. One of them, the electrons should be on the left. One of them, the electrons should be on the right. But ultimately, no electrons in our overall equation. Due to electron flow, chemical changes occur. We have things changing. Substances that are turning into ions, substances that are turning into solids in this case. And then also, like we saw, two half reactions can be added or combined to give the overall equation. Now, I've been trying to stress this, and here it is again. It's all in caps, so it must be important. Number of electrons lost by one half reaction must equal the number of electrons gained in the other half reaction. It does not make sense for there to be more electrons gained than lost. So they have to be the same. All right, so let's talk about the salt bridge. Without the salt bridge, this reaction will not occur. So what happens is positive and negative ions in the salt bridge. So that could be, I said our salt bridge maybe contains potassium nitrate. So potassium ions and nitrate ions migrate through the salt bridge. They go into the solutions in each half cell in order to balance electrical charges. They prevent this movement of ions into the solutions, prevent something called polarization or the buildup of charge. So without the salt bridge, those solutions are going to develop an electrical charge, either positive or negative net charge. And if that happens, the redox reaction will stop and no more voltage will be produced. So we need the salt bridge. All right, so I've been throwing around these terms, oxidation and reduction. So what do they actually mean? Reduction describes a process in which electrons are gained. That doesn't seem to make sense. Reduction, it seems to be that something is decreasing. Well, it's called reduction because this thing called oxidation number decreases. And so we'll learn a little bit later about oxidation numbers. For now, maybe we can just think of it as charge. The charge decreases. So if something is gaining electrons, then we say that substance is being reduced. So what substance was being reduced? Well, it was the silver ions. Now, don't say silver. It's not the silver metal that was being reduced. It's the silver ions. And so notice we're going from +1 charge to 0. The charge is decreasing, and so we say that's the Ag plus is being reduced. And again, notice in our reduction half reaction, the electrons that are being gained are shown on the left side. The opposite of this is called oxidation. Oxidation describes a process in which electrons are lost, and the charge then will increase. So in our reaction in this galvanic cell, the copper metal was being oxidized to copper-2 ions. So we're going from 0 charge to +2 charge. So the charge is increasing. Now, technically, it's this thing called oxidation state or oxidation numbers. And sometimes charge and oxidation numbers are the same. I'll tell you the difference later. All right, so again, also use this term, redox. Oh, you know what? Let's back up. How are you going to remember which is which? Well, we have a couple different sayings that you can use to help you remember. One of them is Leo the lion says grr. Leo says grr. Losing electrons is oxidation. Gaining electrons is reduction. Another one that some students like to use is oil rig. Those things off of the coast of Long Beach, oil rigs. Oxidation is losing electrons. Reduction is gaining electrons. I don't care which one you use as long as you know the difference between oxidation and reduction. All right, here we go again. Redox, short for reduction and oxidation. They cannot happen by themselves, they happen together. Redox is the overall chemical reaction involving the transfer of electrons. All right, now going back to our electrodes, I said that the electrodes have a special name. So let's start with this part here. The electrodes are known as the anode and cathode. All right, we're going to do a lot of word association and letter association here. Vowels and consonants. So let's start with this one. The anode is the electrode where oxidation occurs. So both the word anode and oxidation starts with a vowel. Well, let's go back to our galvanic cell and let's label the anode. All right, so where is oxidation occurring? Well, here's some more letter association. The electrons move away, that word away starts with a vowel, away from what is being oxidized. So where is oxidation occurring? Left half cell or right half cell? Well, the electrons are going to the right, so whatever's on the left side, something there is being oxidized. And the electrode where this process is occurring is called the anode. It's kind of hard to read, but that says anode. So the copper metal here is our anode. Should be noted that in a galvanic cell, the charge of the anode is negative. All right, so we'll come back to letter A in a bit, so fill that in letter B. In this galvanic cell, the copper metal is the anode. The other electrode being the cathode. The cathode, that word starts with a consonant, not a vowel, is the electrode where reduction occurs. Now be careful, your anode and cathode may not be the substance being oxidized and reduced respectively, but they are where the oxidation and reduction processes occur. So the cathode is the electrode where reduction occurs. Let's take a look at our galvanic cell and see which one that is. So where exactly does reduction occur? Now, of course, you can use process of elimination, but let's look at it a little bit further. Again, some letter association. The electrons go towards, that word towards starts with a consonant, not continent, consonant. The electrons go towards what is being reduced. Both the words towards and reduce start with a consonant. So wherever the electrons are going, they're going this way, towards the silver metal. That means the silver metal is the cathode. Now, any guesses what the charge of the cathode is in a galvanic cell? That's right. So sometimes I like to write it like this. It's like, well, that's a weird looking T. Well, trying to make that T look like a plus sign. Cathode in a galvanic cell is the positive electrode. All right, so fill that out in letter B. The silver electrode is our cathode. All right, going back to the salt bridge. Let's look at what exact ion from the salt bridge goes into which solution. Let's start off in our half cell on the left. So what's going on here? We have copper metal that is turning into copper 2 ions. So what's happening is we're increasing the number of positive ions in that solution. That's not good. So how can we keep this solution neutral? Well, we have to balance out that increase in positive charge with negative charges. So the negative ions from the salt bridge, and again, if let's say, that's kind of hard to read, but let's say this is a potassium nitrate solution in here. The negative ions are going to go into this solution to balance out the increase in the positive charge of that solution. Well, what do we call negative ions? Negative ions are called anions. So here we go again, another word association. The anions from the salt bridge are going to migrate towards which electrode? The anode. They're going to go into the solution where the anode is to keep that solution neutral. What's happening on the other side? So we have silver ions that are turning into silver metal. Silver ions are being reduced. And so what's happening is we are decreasing the amount of silver ions in solution. So that solution is becoming then less positive, I guess, right? Or more negative, however you want to look at it. And so how can we keep that solution neutral? Well, if we're losing positive ions, those lots of Ag plus ions need to be replaced with some other positive ions, namely potassium, K plus, if that's what's in our salt bridge. What do we call positive ions? They, of course, are called cations. So the cations in the salt bridge go towards which electrode? They're going to go towards the cathode. So anions go into the solution where the anode is. Cations go into the solution where the cathode is. And again, both of these go in their respective solutions in order to keep those solutions neutral. All right, so make sure to fill that out in your notes. Next up, some more vocabulary. Be careful, a lot of times students mess these up. Oxidizing agent. Seems like a fancy word. The oxidizing agent is the chemical that causes something else to be oxidized. It causes something else to lose electrons. Well, how does it do that? Well, if it's causing something else to lose electrons, it itself must be gaining those electrons. So the oxidizing agent is itself reduced. Well, let's take a look at our overall equation again. So what is being oxidized? Well, the copper metal is being oxidized. Well, what is causing the copper metal to lose electrons or to be oxidized? That would be Ag+. So Ag+ is our oxidizing agent. Another term for an oxidizing agent is oxidizer. So Ag+ is the oxidizer here during this reaction. Likewise, we have something called a reducing agent or reducer. The reducing agent is the chemical that causes something else to be reduced, causes something else to gain electrons. Well, how can it cause something else to gain electrons? Well, it itself must be losing those electrons. So the reducing agent itself is oxidized. So again, let's go back to our equation and see what's happening here. So what substance is being reduced? I'm kind of out of space here. Ag+ is being reduced. Now notice something. Those terms, oxidation and reduction, they refer to the reactants. Likewise, the reactants in a redox reaction are known as oxidizing agent and reducing agent. So the Ag+ is being reduced. What is causing that to gain electrons? Well, the copper is causing that. So the copper is our reducing agent. So go ahead and fill that out in your notes. All right, so I'm going to do a demonstration where I'll set it up for you now and then I'll show you in a bit, where I'm going to take these two metals, zinc metal and copper metal, and I'm going to put them in different solutions. So I'm going to take a piece of zinc metal, put it in a solution containing silver ion, so silver nitrate. I'm going to put it in a solution containing copper 2 ions, so copper 2 sulfate. I'm not going to put the zinc metal, though, in a solution of its own ions because zinc and Zn+2 are not going to react with each other. And then I'm going to put the zinc metal in a solution that contains H+, that being hydrochloric acid. I'll do the same thing with a copper, piece of copper metal in a solution of silver ions. I'm not going to put copper in a solution of its own ions. Copper metal in a solution of zinc ions, and copper metal in the hydrochloric acid solution. And then we're going to see, when does a chemical reaction occur? Which reactions occur? And that's going to tell us something about the ions, these ions here, Ag+, Cu+, 2Zn+, and H+, and their ability to be reduced, their ability to gain electrons. So that'll be for next time. So we'll go ahead and stop this lesson here. Thanks for watching.